Okay, let's move to chapter number 7. Number 7. Okay, uh, let's review the chapters on this textbook. Yeah, we finished the chapter 1, statistics basics, uh, graphical description of data, examine the evidence using graphs and statistics. And we finished the probability. Yeah, sure. Probability, I just checked the first and the second section. The number 3 is not so important for us. And chapter 5, discrete distribution. And chapter 6, continuous probability distribution. And now we are moving to the chapter number 7, one sample inference. One sample inference. In short words, we try. What does it mean? Sample. Sample is in contrast to population. Population means the whole, the complete icons or people or something over there. But it's impossible for us because we have only limited money, we limited labor. It's impossible for us to investigate every member in the population. Thus, we try to select some useful information. That is called sampling. And now, chapter number 7, try to use sample to interfere the big population. Again, we try to use limited information to interfere to guess the big population. For example, the U.S. president election toll. Yeah. Before the election, there are many surveys ask the voters, who do you want to vote? Who do you want to vote? And it's impossible to ask every, do you like the Joe Biden? Do you like the Trump? Donald Trump? Okay. It's impossible to ask everyone their voting tendency. Thus, sampling, how to do the sampling, that is very important. That is very important. Okay. And now let's move to our one sample inference. One sample inference. Now you have all this information about the descriptive statistics and probabilities. It's time to start inferential statistics. Inferential with limited information, with small amount of information, try to interfere the big information. Okay, there are two branches of inferential statistics: hypothesis test and confidence intervals. Okay, again, hypothesis test and confidence intervals. There are two branches. There are important components of this one. Okay, the first one, definition 7.1, hypothesis test. Make a decision about a perimeter based on a statistic or plural S. Again, hypothesis test. Make a decision about a perimeter based on a statistics. Okay. Second one, confidence interval. Estimating a perimeter or perimeters based on statistics. I know it's not easy to understand, but now confidence interval, estimate a perimeter based on, okay, let's move. Chapter 7.1, chapter 7.1, okay, basics of hypothesis test, let's move. Okay, first one. To understand the process of hypothesis test, you need to first have an understanding of a hypothesis, what the hypothesis is, which is an educated guess about a perimeter. Once you have the hypothesis, you collect data and use the data to make a determination to see if there is enough evidence to show the hypothesis is true. However, hypothesis testing, you actually assume that something else is true. And then you look at your data to see how likely it is to get an evidence, event that your data demonstrates with the assumption. If the event is very unusual, then you might think that your assumption is actually false. If you are able to say this assumption is false, then your hypothesis must be true. This is known as a proof of contradiction. You assume the opposite of your hypothesis is true and show that it cannot be true. If it happens, then your hypothesis must be true. I know it's a bit complicated, but later when I have some real cases, examples, then you will understand it. Okay, let's move to this one. Example 7.1.1, basics of hypothesis testing. Suppose a manufacturer of Ch7.1 battery claims the mean life of the battery is 500 days. Okay, the claim of that the use a very long life. When a standard deviation about 25 days, you are the buyer of this battery and you think this claim is inflated. Is inflated. You would like to test your belief because without a good reason, you can't get out of your contract. Okay, what do? The first one, well, first you should know what you are trying to measure. Define the random variable let x equals life of an Ch7.1 battery. And now you are not just trying to find different x values. You are trying to find what the true mean it is. Since you are trying to find it, it must be unknown. You don't think it is 500 days. If you did, you wouldn't be doing any test. The real mean mu, the true mean mu is unknown. The mean here is for the population. Again, mu is the population mean. The other one, x bar, is the sample mean. Again, sample a small amount, population the big amount, a complete body. That means you should define that too. That mu equals mean life of an Ch7.1 battery. Now what? You may want to collect a sample. What kind of sample? You could ask the manufacturer to give you batteries, but there is a chance that there could be some bias in the batteries they pick. Oh, okay, those batteries are for my potential customers, and I will try to pick up some strong batteries for them. And it can be a bias. Okay, to reduce the chance of a bias, it is best to take a random sample. How big should the sample test? A sample size 30 or more means that you can use central limit theorem. Okay, the central limit theorem, the sample size of 30 is reasonable. Pick a sample size of 30. Example 7.1.1 contains the data for the sample you collected, like this one. For 90 days, the life of them, 503, 792, 282, like this one. And now, what should you do? Look at the data set. You see some of those times are above 500 days and some are below. But looking at all of the numbers is too difficult. It might be helpful to calculate the mean for this one. Okay, here, the sample mean X bar is 490 days, 490 days. Again, here, the simple mu is the population mean. But it's impossible to get all population mean. It's impossible because we don't have enough money and labor and time. Thus, this question pick up 30 factories to test the life of that. After the test, we the author got this information, and the sample mean is X bar equals 490 days. Looking at the sample mean, one might think that you are right. However, the standard deviation and the sample size are also play a role. So maybe you are wrong. Okay. Again, let's review the question. The manufacturer claim the battery life is 500 days, and the standard deviation of that is 25 days. It means all population 500 plus minus 25 days can cover 68% of the samples. Okay, of the items. Okay. But besides the means, the standard deviation and sample size are also important. Before going any further, it is time to formalize a few uh, definitions. And you have a guess that the mean of life battery is less than 500 days. This is opposite to the claim, the manufacturer's claim. There really are two hypotheses, are just guesses. Here, the one that is the manufacturer claims and one you believe. This have to have the names of that. The first one, non-hypothesis. Historical value, claim, or production specification. The symbol is H0. Non-hypothesis. Non means nothing. Zero. Okay. And the second one, alternate hypothesis. What you want to prove. This is what you want to accept the truth when you reject the non-hypothesis. And there are two symbols of the commonly used for that one. Alternate hypothesis, HA, or HI. And the symbol HA will be used in this book. In general, the hypothesis looks something like this one. Non-hypothesis H0, mu equals mu0. Non-hypothesis or alternate hypothesis, mu, the population mean, less than mu0, where mu0 just represents the value of the claim size on the population is actually equal to. Okay, the second one. Also, HA can be less than, greater than, or not equal to. Okay. Okay, let's move to next one. For this problem, non-hypothesis mu equals 500 days, since the manufacturer says the mean life of the battery is 500 days. Alternate hypothesis mean less than 500 days, since you believe that the mean life of the battery is less than 500 days. Okay. Now, back to the mean, you have a sample means of 490 days. Is this small enough to believe that you are right and the manufacturer is wrong? How small does it have to be? Let's check. If you calculate sample mean of 235, you will definitely believe the population mean is less than 500 days. But now they got 490. But even if you have a sample mean of 435, will probably believe that the true mean was less than 500. What about 745? Sorry, 475, for example, all for 483 days. And there are some points where you would stop being so sure the population mean is less than 500. 500. That the point separates the value from where you are sure and pretty sure that the mean is less than 500 days. Okay, let's move. Let's move. And well, it depends. Okay, I'll move this. This is a little bit boring. You want to find the probability, the sample mean x bar less than 490 hypothesis is true. The hypothesis is true. To compute this probability, you need to know how sample mean is distributed. Since the sample size is less than 30, when you know the sample means is approximately normally distributed, remember the sample mean, the sample standard deviation is a sigma divided by square root of n. Okay, a picture is always useful like this one. Okay. Before calculating the probability, it is useful to see how many standard deviations away from the mean the sample mean is. Using the formula of the z-score, yes, we taught that last week. On chapter 6, you will find z-score like this. And 490 subtract 500 divided by sigma over square root of n, square root of n, and the answer is minus 2.19, minus 2.19. Okay, this sample mean is more than 2 standard deviation away from the mean. It says the pretty far, and you should look at the probability too. The probability is close to 0.0142. How does it mean? The probability less than 2%, only 1%, 1.4. The probability is very, very low. Okay, there is a 1.40% chance that you could find a sample mean less than 490, when the population mean is 500 days. That is really small. So the chance and the assumption the population means 500 days is wrong. And you can reject the manufacturer's claim. Okay, the purpose is to accept or to reject the manufacturer's claim. But how do you quantify real small? 500, 5%, 10%, or 15%? Really small? How do you decide? Before you answer the question, a couple more definitions are needed. The first, test the statistic z equals this one, the formula like this, since it is calculated as a part of testing of the hypothesis. Okay, the second one, p-value. Okay, p-value, this one is very important, very, very super, extremely important. Okay, probability that the test statistic will take on more extreme values than the observed test statistic. Given that the non-hypothesis is true, it is the probability that was calculated above. Again, p-value, the p, it means probability. And now, I will be quiet for 1 minute. Please remember the definition of p-value, because in the future, we will check the p-value for many times. And your background is statistics and business. You need to know the definition. Okay, I'll be quiet for 1 minute. Okay, let's move. And now, how small is small enough? The answer is like this. Look at this. And there are actually two errors can be made. Sure, two type of error, alpha and beta, is really complicated. And now, be patient. This is my lecture. Okay. The first error, if you say that non-hypothesis is false, when the fact is true. What's the probability? Then this means you reject the non-hypothesis when it was true. You made mistake. You made a mistake. And the second error, if you say non-hypothesis is true, but in fact that is wrong, that is false, that means you fail to reject it when the non-hypothesis is false. When the non-hypothesis is false. Two types of errors. The first one, when the non-hypothesis is true, you should accept it, but you reject it. It's called type 1 error. If you fail to reject, you accept it, you did not reject it, no error. Okay, the second one, when the non-hypothesis is false, theoretically, you need to reject it. But you fail to do that, you accept it. It's type 2 error. Type 1 and type 2. Okay, let's check alpha and beta. Okay. The definition, type 1 error is rejecting non-hypothesis when that is true. Okay, that's type 1 error. Type 2 error, failing to reject non-hypothesis when that is false. That is false, but you didn't reject it. Okay. Then now, since there are two errors, one can define the probability attached to each error. The first one, alpha. Alpha is the probability, type 1 error, when you reject it, but in fact that is true. What's the probability? The second one, beta, the type 2 error, when that is false, you should reject it. Instead, you fail to reject. In other words, you accept that. Alpha 1 is called the level of significance. Okay. Another common concept that is used, the power. The power is 1 minus beta. 1 minus beta. Now, there is a relationship between alpha and beta. There are not a complement of each other. How they related? How are they related? If one alpha increases, that means chance of the making type 1 error will increase. Again, if alpha increases, that means here it means okay, it's not the average. Okay, it means the chance of making type 1 error is increases. Okay, it's more likely that the type 1 error will occur. Alpha occur. Okay, it makes sense that you are less likely to make the type 2 error only because you will be rejected more often. Okay, you will be failing to reject non-hypothesis less. Okay, let's skip this one. Okay, consider you have a larger sample that representative of the population. Now it makes sense that you have more accuracy when a smaller sample, or with a smaller sample. Think of this a way which will you trust more? A simple mean of 490. If you have sample size 35, size of 350, assuming a representative sample, of course, the 350 because there are more data points and some more accuracy. If you are more accurate, then there is less chance you will make an error. By increasing the sample size and representative sample, you decrease both alpha and beta. Okay, now for a certain sample size, n, sample size n is a italic, if alpha increases, beta decreases. For certain level of significance alpha, if if n increases, beta decreases. Now, how do you find alpha and beta? Alpha is actually chosen. There are only three values are usually picked up from alpha 0.1, 0.05, and 0.1. Beta is very difficult to find, so it is usually not found. If you want to make sure that it is small, that you take as large as a sample as you can afford, provided it is a representative sample. This is one of the power. You want beta to be small and the power of test is large. The power word sounds good. Okay. Again, generally, there are three types of alpha: 0.01, 0.05, and 0.1. Generally, 0.05 is the most common used one. Okay. I think I will skip this one. Okay. Let's check this example 7.1.4. Identify the hypothesis necessary to test the following statement. First, the average salary of a teacher is more than $30,000. Okay, it's a statement. Okay, identify the hypothesis necessary test for this one. The second one, the proportion of students who like math is less than 10%. Do you like this statement? Is it true or not? Okay, let's check the A. Solution: X, salary of teacher. Mu, the mean. Okay, the mean of salary of teacher. And the guess is the mean is greater than $30,000, and that is the alternative hypothesis. And the null hypothesis is the same perimeter and number with equal sign. And here, null hypothesis mu equals $30,000 of the teacher salary. The second one, alternative hypothesis mu greater than $30,000. Okay, let me finish this section, then we will have 10-minute break. X, the number of students who like math. 1 minute, please. The P, the proportion of students who like math. Okay. And here the guess is the population. The probability less than 0.1. The hypothesis probability is 0.1. They love math. And the alternative hypothesis value, the p-value less than 0.1. Okay. I think we can stop here and then move to the next section. Okay. Okay, have a 10-minute break. And next class, I will distribute your exam paper and explain the questions.